Okay, so we want to talk about numerical approximation of PDEs, and we'll get started here with an introduction and approximations of first and second derivatives. So there's a little introduction. It's hard to solve PDEs explicitly, so we're going to use what's called a finite difference method. And we need to approximate the first and second derivatives because our PDEs involve first and second derivatives. So we're going to come up with the approximations for the first and second derivatives here, and in the videos after that, we'll go through particular examples. So we want so what we want is an approximation of the derivative in terms of the function. So remember that the definition of the derivative is this. We're at a point A in the domain of the function. So it's supposed to be A plus delta x minus f of A over delta x. So this is the definition of the derivative. So what we want to be able to do is say, well, the limiting process saying that exists means for quote unquote small enough delta x, and that small enough, whatever that means, that is determined by context. What purpose you're using things for. For small of delta x, f prime of A equals f of A plus delta x minus f of A over delta x. Oh, it's a little squiggly line there to mean approximately so. So that's the approximation of the first derivative, right? So if we know A, if we know the function and we go a little bit to the right of a point A, we'll get the first derivative. Okay, approximating the second derivative now. I'll just pull this up a little bit so we've got some space. So we want to now know, this is a little bit trickier, the second derivative in terms of the function f. So just as we have the first derivative in terms of the function here, oh, that's a delta x on the bottom, we can figure out the second derivative in terms of the function. So to simplify things a little bit, notation, I don't want limits everywhere. We'll put f prime of x equal to some function p of x. Why that simplifies things is that means that the second derivative is the first derivative of p. So f double prime at a particular point equals the limit as delta x goes to 0 of p of x plus delta x minus, I keep forgetting the a, p of a plus delta x minus p of a over delta x. Okay, but p of a plus delta x equals f prime at the point a plus delta x, and that's the limit as delta x goes to 0 of f of a plus delta x, that's the point that we're at, plus another delta x minus f of a plus delta x over delta x. Right? And that's just using this again, but I've put a plus delta x in for my a everywhere. Okay. And we also need p of a. Oh, let's put that thing up here. So P of A, now that's f prime at A. That's the limit as delta x goes to 0 of f of A plus delta x minus f of A all over delta x. So f double prime of A, what's that? That equals the limit as delta x goes to 0 of 1 over delta x, and that's this delta x here, times P of A plus delta x. P of A plus delta x is this whole thing, and there's a limit as delta x goes to 0 of this fraction minus this fraction. So f of A plus 2 delta x, because there's 2 delta x's here, minus f of A plus delta x, minus this fraction, minus f of A plus delta x, minus f of A, all over delta x. So I'm going to be a little loose with the delta x's here. We've got a number of limits. So I'm going to take this limit out because it's just taking this limit as delta x goes to 0. And then you take the limit again, so we can actually just combine those into one limit, and then we end up with an f of A plus 2 delta x minus 2 f of A plus delta x minus f of A all over delta x quantity squared. Right, so this delta x times that delta x, we take the limit as delta x goes to 0 of this, and that's defined because we assume that we have a second derivative, and this is actually first derivative, and then we take the limit again, and so since all the limits are defined, we can take this limit and combine it with that limit, just essentially move the 1 over delta x inside, take the limit as delta x goes to 0 of the whole thing. Now, if we're thinking about what's going on here, we've got a function and 3 points, a plus delta x, and a plus 2 delta x. And we've got 3 points like that. And this width is delta x, this width is delta x. So we take this and that, and we want to be able to read off the concavity at the middle point by taking, actually this sort of reads off the concavity at A by taking these points. And so it's looking at the difference between, approximating the difference between these slopes a little bit. So anyway, what we want to be able to do is actually write this so that we're actually looking at A plus delta x as being the center rather than A. So f double prime at A equals limit as delta x goes to 0 of f of A plus delta x minus 2 f of A minus f of A minus delta x all over delta x squared. So what we're doing here is, instead of looking at the limit as of these 3 points and thinking of them as centered, and instead of thinking of this limit as being A plus 2 delta x and A plus delta x, what I'm going to do is think of it as centered here and think of it as A plus delta x, A plus delta x plus delta x, and A plus delta x minus delta x, which gives you A. So that's just relabeling these things. It's the same 3 points and same thing fractions, except we're just going to think of this as being the center A. And as the limit as delta x goes to 0, we'll end up getting the same thing, because as delta x goes to 0, this whole picture moves over. But this makes it a little bit easier to state. So the second derivative at a particular point is roughly equal to f of a plus delta x minus 2 f of a minus f of a minus delta x over delta x squared, as long as delta x is quote unquote small enough.